Welcome to The Explainer, where we break down complex topics into clear, engaging explainers.
All right, let's kick things off with a number. And this number is, well, it's so big it's almost impossible to wrap your head around. 35 to the power of 100. You know what that is? That's roughly the number of possible move sequences in just one game of chess.
And just to put that into perspective for you, that number is bigger, way bigger than the estimated number of atoms in the entire observable universe. I mean, just think about that for a second. So that leads to a pretty huge question, right? How on earth can a computer, an AI, possibly wade through this astronomical number of options to play a game like chess? I mean, never mind just playing. How can it actually plan a winning strategy against that kind of scale?
Well, the first logical step, the first attempt at cracking this, was to build what you might call a perfect player. The idea was, what if we design an algorithm that always plays the perfect move? And to do that, it has to assume its opponent is also a perfect player.
This approach is called the minimax algorithm, and it's a really big deal in AI and game theory. The whole thing is built around searching through all the moves in what's called a zero-sum game. All that means is, it's a game where if one player wins, the other one has to lose. My gain is your loss. So, Minimax pictures the game as a kind of duel. You've got two sides. On one side, there's the maximizer. Let's say that's our AI. Its only goal is to get the highest score possible. And on the other side, the minimizer. That's the opponent, and their only goal is to do the exact opposite, to force the lowest possible score for our guy, the maximizer.
So, how does it do this? It explores something called a game tree. Basically, it maps out all the possible moves and countermoves, looking ahead all the way to the end of the game. And at the very end of each branch, what we call the leaf nodes, it assigns a score. Think of it as a final value from our maximizer's perspective. You know, high scores mean we're winning, low scores mean we're losing. Simple as that.
Okay, so here's the clever part. Minimax doesn't start from the current move. It actually starts at the end of the game and works its way backward. So it looks at the final turns. Whenever it's the opponent's turn, the mind player's turn, the algorithm makes a simple assumption. The opponent will always choose the move that leads to the absolute worst score for us. As you can see here, from each little group of possible end scores, mine picks the lowest one.
Then the algorithm moves back one more step to our turn, the max player's turn. Now, Max looks at the options, knowing exactly what Min is going to do in each case. So from those terrible outcomes that Min has picked out for us, Max gets to choose the best one, the one with the highest value. It's literally picking the maximum of the minimums, the best of all the worst-case scenarios. And that right there, that's the minimax move.
Now this method is perfect. I mean, by checking every single possibility, Minimax guarantees you'll find the absolute best move. But, and this is a huge but, this perfection comes at a totally crippling cost.
And this is its fatal flaw. The problem is that the number of things it has to check grows exponentially. What does that mean? It means that looking just one single move further into the future doesn't just add a few more calculations, it multiplies the total workload over and over again.
Yeah.
In computer science jargon, we call this O of B to the M complexity. But forget the letters. All it means is that for a game like chess, which has, around 35 possible moves each turn, looking even just a few turns ahead creates this massive computational explosion. It's way, way too slow to actually work in the real world.
So, that's the big puzzle, isn't it? How can we get that same perfect answer that Minimax promises, but, without doing all of that impossible work? How can we be both perfect and fast?
Okay, and this is where something truly brilliant comes into play. Alpha-beta pruning. Now, this isn't a whole new algorithm. Think of it more like a super smart upgrade for Minimax. Its whole job is to intelligently prune or cut away entire branches of that game tree that it can prove are completely irrelevant to the final decision.
It does this by keeping track of just two values, alpha and beta. And it's actually pretty intuitive when you think about it. Alpha, that's the best score our player, Max, is already guaranteed to get. It's our floor. We know we can get at least this much. Then there's beta. That's the best score the opponent, Min, is guaranteed to hold us to. Think of it as their ceiling. They can definitely keep our score at or below this number. The whole trick is in how these two numbers interact.
All right, check this out, because this is the core idea, and it's so smart. Let's say our AI is looking around and it finds a path of moves that guarantees it a score of 10. Awesome. So now our alpha value, our guaranteed floor, is 10. Then we start exploring a totally different path, and right away we see that on this path, the opponent can force a situation that leads to a score of 3. We can just stop looking instantly. Why? Well, because we already have an option that gets us a 10. Why would we waste any more time exploring a path that we already know is going to be worse? We just wouldn't. So chop, we prune that entire branch. Done. We don't even look at the rest of it.
Okay, so theory's one thing, but seeing it in action really makes it click. So let's do that. Let's walk through a search step by step and see exactly how this pruning works.
So the search starts by diving deep down the leftmost branch, all the way to the bottom. Here, a max player node is looking at its choices. 2 possible outcomes, a score of 8 or a score of 1. Well, it's a maximizer, so what's it going to do? Of course, it chooses the 8.
Okay, now that 8 gets passed back up the tree to its parent node, and this parent node is a min player. So the min player looks at this and thinks, okay, I know that if I make this move, I can hold my opponent to a score of 8, or maybe even something better for me, something lower. So it sets its beta value, its ceiling, to 8. For now, that's the best outcome it knows it can force.
All right, now stay with me. That same MIN node, which has a beta of 8, starts exploring its other child. This next branch down is a max node, and it looks at its first move and sees an outcome with a score of 7.
So this process keeps bubbling up the tree. And let's say after all that, the value that gets passed all the way up to the root, the very top max node, is a 7. This is a big moment. The root has now fully explored its first major branch. It now knows it has a move it can make that will guarantee it a score of at least 7. So what does it do? It sets its alpha, its floor, to 7.
And now, here comes the magic. The root node, remember, its alpha is 7. It knows it can get a 7. So it starts exploring its next major branch. It goes down a bit, and the min player on this new path finds a move that results in a score of just 2. It sets its beta value to 2. Now, the check happens. The root node looks at this and says, hold on, my alpha, my guaranteed score is 7. But on this new path, the opponent can hold me to a beta of 2. Since 7 is bigger than 2, there's absolutely no reason to explore this path any further. The root will never choose this move. And prune. The moment alpha is greater than or equal to beta, we cut the whole branch off. All those other possibilities down that path, we don't even look at them. We just saved a ton of time.
And that right there is the incredible power of this whole thing. You see, we're not just snipping off 1 or 2 bad moves at the end of a branch. No. We are chopping off entire subtrees. We're ignoring potentially millions or even billions of calculations in one go. And this is what takes a problem that seems computationally impossible and makes it totally solvable.
Which kind of leaves us with a pretty cool final thought, doesn't it? We started out with this mind-bogglingly huge number, the complexity of chess. And it seems like you'd need a supercomputer the size of a planet to solve it. But what alpha-beta pruning shows us is that maybe, just maybe, real intelligence isn't about having more processing power. Maybe it's about having the wisdom to know what to ignore.